I'm going to share with you my understanding of, or actually how I reason out the theorem, the second integral theorem called the Divergence Theorem or Gauss's theorem. And that theorem is defined as the integration over the entire volume V of the divergence of a vector should be or shall be equal to the integration over the surface that define the volume of that same vector as it is multiplied with the unit area. So these are, this is a scalar, this is a vector and the vector, but the product here is a scalar. And how it fits into the Maxwell equations, this part here is called the Gauss's equation. So once you establish that this part is equal to this part, you can see that this part is equal to this, and because volume V is any arbitrarily defined volume, so that means you can scale it down to the point where you say divergence of D is equal to rho, which is the density of charge at any point in the area of interest, right? So pretty much the same reasoning like what we did for the curl and the other theorem, which is defining the integration of curl within a surface equal to that the integration of that vector around the curve of that space. Okay, so so similar to the Stokes theorem. So by definition, divergence of D is defined as the part within the parentheses here, and dV as a unit volume is equal to the three part dx, dy, and dz, right? So let's say that we redefine and visualize that the divergence of D multiplied by the unit volume, which is infinitely small here, would be the sum of 6 components, and within for the x direction it will be a surface dA1 and a dA2, and then we look at the vector d1 at the left side and the d2 at the right side, and then we repeat this for the y and the z component. Now once we establish this, then later on we can use this and say for adjacent cubes or unit volume, all the flows out of one into will be cancelled by the flows that goes into the other one, simply because you have the same vector, but the normal vector of this surface is exactly opposite to the normal of the other surface, right? So once we reason that out, then what is left would be just the product of the vector times the unit area, which is facing outward of the volume. Thus, once you aggregate everything, what you get left is just the surface area, the integration of D times the unit areas that are facing outward outside of the volume, and thus this theorem holds, right? So with respect to just the x-axis, we would have d2 equal to dx, which is here, plus a small change, which is equal to the rate of change, which is derivative of dx with respect to x times how much change, right? And then because the surface area here is perpendicular to the axis x, so the area is dy dz. And because our convention of surface area facing outward, so this is a plus sign. On the other hand, on the other opposite surface, we have also dx, which is what the value of the vector d at that time, the x-axis component of that vector, but the area of the unit surface here is also dy times dz. However, there's a minus sign here because in our direction, that unit area is pointing the opposite direction. That's why it has a minus sign. All right, so the sum of these is the algebraic sum of both of these, and you can see that this part cancel this part, and what is left is just this times this times this and this, and this is exactly what this one times this, right? So, well, in my mind, at least this thing is equivalent to the definition of the divergence of D times the unit volume. Now, when you take that integration over the entire volume of interest, then all the internal phase, any value that associated with any internal phase will be cancelled by the adjacent unit, volume unit, right? Because as I said, the same vector, but one surface is facing oppositely to the other surface. So, and that left all the outside, which basically will go back to the integration of the value of d times the area, but you take it over the entire surface area. So there you go. That's the understanding of how the Gauss's theorem or divergence theorem works. And in this particular case, what we have is we have integration of a d over the area, the float of some vector going into the area of a volume equal to the divergence of that vector, or the summary of all the divergence within that volume. Thanks for listening. Bye-bye.